In this video, we're going to continue our discussion of limits, and we're going to talk about ways you can evaluate limits algebraically. So we've defined a limit, we know what it is. We've also talked about how you can find a limit graphically and how you can find one numerically. So the general idea with a limit is we're taking a limit as our x values approach a certain number, and in finding a limit, we're asking the question, as our x values behave in this way, how are our y values behaving? So if we look at this particular x value in question from both sides, if the corresponding y values are also approaching a common value, then that common value among the function values represents what we call the limit of our function as x approaches that certain number in question. So we talked about how we could find limits graphically, numerically, what that looks like on a graph, and then also how we can generate a limit just by generating x values that grow increasingly close to whichever value we're interested in terms of where our x values are approaching. So as we determined in a couple of cases, whenever we have a specific function that behaves in a specific way, then finding a limit can also be the same thing as just evaluating a function. So in certain cases, for the x value in question, the limit at that x value is also the same as the function value at that x value, the actual associated y value. And as it turns out, we can actually formalize that. So for any rational function f, now keep in mind rational does not have to mean it truly has a numerator and denominator, it just means it doesn't have any irrational components to it. But for any rational function, as long as this number a is in its domain, it is something for which the function is defined, then we can evaluate our limit in this way. So if we want to evaluate the limit as x approaches a, again specifically where this number a is in the domain of our function f of x, then it turns out that the limit is actually going to be the same thing as the function value. So what this means essentially is that as long as f of a is something that is actually defined, then another way to find the limit aside from looking at the graph, aside from generating the limit numerically, is just by plugging in a. If we plug it in, then the output we get is going to be the same as the value for the limit, as long as the value of a is something that is in the domain of our function. Now, as we determined when we were looking at limits for specifically functions that have discontinuities, where there's holes in the graph, there are breaks in the graph, those kinds of things, in a lot of situations we're looking at a limit from the perspective of some x value that is not in the domain of our function. So if we're talking about, for instance, an x value that represents the location of a vertical asymptote, where there's a big break in the graph, there's a big hole in the graph, then those particular x values don't represent numbers within the domain of the function, and plugging them in directly is not going to be an option. So if we're talking about an x value that is outside of our domain, it is possible that there is still a limit, but we won't be able to evaluate it by just plugging in the x value that we're interested in to our function. So if that is the case, if we're in that situation, we're going to potentially have to use some additional algebra to maybe simplify our function, write it in a different way, manipulate it, or in certain cases, algebra just will not be a good option for finding our limit, and we'll have to fall back on our other techniques. So we'll have to find it numerically, or graphically, or some combination of the two. So in a lot of cases, finding a limit algebraically will save us a little bit of time, but it's good to have multiple strategies to use, because if anything, having 3 different strategies to solve a problem means you also have ways to check your work. If for some reason one of the limits you find is not consistent with the value you find using other techniques, then that's an indication that you probably need to go back and check your work and you potentially have made a mistake. So let's look at a couple examples. So the first example, we want to find the limit as x approaches 2 of this particular function, which is a polynomial function. So notice it's slightly different notation than what we've used before. Here we actually have the function rule subbed into the limit rather than just using the standard f of x notation. This is acceptable as well. This is another way to write a limit, specifically when we want to indicate what the rule is in that limit notation. Now, because this is a polynomial function, more generally it is a rational function, every polynomial function has a domain of all real numbers. So that means by default, x equals 2, the number in question, is within the domain of this function. So based on that, to evaluate this limit, all we have to do is sub in x equals 2, find the associated function value, and that's going to be the same as the value for the limit at that particular value of x. So I'm going to sub in 2. So 2 to the 4th power minus 5 times 2 cubed plus 2 squared minus 7. Simplify all of that down. So 2 to the 4th power is going to be 16. Okay, 2 cubed is 8 times 5 is going to be 40. 2 squared is 4. Okay, minus 7. Let me put that into the calculator. 16 minus 40 plus 4 minus 7. And of course you can evaluate the whole thing in the calculator if you want. That's perfectly fine. And that is going to be negative 27. So based on this rule and based on the fact that this particular x value is within the domain of this function, that tells us that this limit evaluates at negative 27. Now, ideally we would like to verify this. This can be easily verified either by graphing the function or by using a numerical technique. So let's verify that this does actually work out the way we're saying it will, just based on specifically a numeric technique. Let's look at that. So I want to graph this function. So we have x to the 4th power. Now be careful when you type this in. Notice my cursor is still in the exponent. You'll want to arrow out, tab out of the exponent before you keep typing. Otherwise, it'll just keep typing in the exponent. So be aware of that. Same problem there. Okay, plus x squared minus 7. And then I'm going to graph that. Okay, so it is a polynomial function. There is a gap there in the graph, but keep in mind that's not really there. It's just because we're zoomed in a particular way. So polynomial functions, no breaks, no holes, nothing like that. Now we want to evaluate this limit specifically at x equals 2. So let's look at the table. So there at x equals 2, notice we have a value of negative 27, so that makes sense with what we just did evaluating at x equals 2. Now to the left-hand side of 2, at x equals 1, our output is negative 10. At x equals 3, our output is negative 52. So those values independently are not enough to indicate that we are approaching a value of negative 27 as we approach an x value of 2. So let's do what we did the last time. Let's go back and change the table settings so that the independent variable is set to ask, so that we can sub in the specific x values we want so we can see the kind of behavior we want. So if we're evaluating a limit at x equals 2, what we want to observe is the behavior for x values that are smaller than 2 but really close to 2, and then also values that are larger than 2 but again really close to 2. So numbers that are smaller than 2, maybe something like 1.9, 1.99, just a little bigger, 1.999, again just a little bit bigger. And what we notice with the y values is that they are getting more and more negative, and they're also getting closer and closer and closer to a value of negative 27. If we wanted to go a little bit further, there we go. We don't actually, well in this case, yes, we do actually reach negative 27, but 1.9999 does not actually evaluate at negative 27. Essentially, it's so close to negative 27 that your calculator can't handle it, can't write what the actual value would be, so it subs in negative 27, even though that's not quite the y value right there. But that is a good confirmation that we are approaching negative 27 as our x values approach 2 from the left-hand side. Now we know limits are two-sided. We have to be able to see the same behavior on the left and on the right. So what we've just demonstrated right here, remember, is what we call a left-hand limit. So if we're looking at the behavior from the left-hand side of our x value, then we're looking at a left-handed limit. We also have to be able to see the same behavior with a right-handed limit, approaching from larger x values. As long as they meet in the middle at the same value, that's our indication that our limit has that particular value. So let's look at numbers that are then larger than 2. So larger than 2 but close to 2. So maybe something like 2.1, which is fairly close. 2.01 is a little bit closer. 2.001, even closer. And again, we're seeing the same kind of behavior. So notice we're also approaching negative 27 from the other side. So because we're approaching that same common value both from the left-hand side and from the right-hand side of x equals 2, that's our confirmation that this limit value does make sense. Now let's look at another one. So for this next function, this function isn't actually rational. This is an irrational function. But as it turns out, sometimes this rule will work for irrational functions as well, as long as we're talking about values within the domain of the function. So we want to evaluate the limit as x approaches 0 of the square root of x squared minus 3x plus 2. So what happens if we just substitute this particular x value? Let's see what we get. So subbing it in, we have 0 squared minus 3 times 0 plus 2. Okay, so those first two terms under the radical, those just evaluate to 0. So all we have is 2. So the square root of 2. So we're saying supposedly this limit evaluates to the square root of 2. Well, what is the square root of 2? Let's see. It is an irrational number, but let's approximate it. So the square root of 2 is approximately 1.41. So we're saying this limit roughly goes to 1.41. As we approach x equals 0, the associated function values are going to approach roughly 1.41. Now, because this is an irrational function, we shouldn't necessarily assume that the same rule applies as applied to this polynomial function above to something that is rational. But again, we can verify the value for this limit by using a numerical technique. So let's graph this one as well. So square root of x squared minus 3x plus 2. Okay, so there's my graph, kind of a strange looking graph. Let's go into the table. Okay, now notice the table, we've got these individual values, we've got some errors, okay, because those are going to be values for which this particular function is undefined, but none of those values are around 0, so those values aren't going to help us. Now in order to clear this out, let's see, I'm going to go back and I'm going to change the table settings just to refresh it. So I'm going to go back and change to auto, and then go back into the table settings one more time, and change to ask again. And notice that's cleared out and we have a fresh table so we don't have any distracting numbers. You may want to do that from time to time. Okay, so we're looking at behavior around x equals 0. So we're asking the question, what's happening for values that are smaller than 0 but very close to 0, and then also values that are larger than 0 but very close to 0. So smaller than 0 would be something like maybe negative 0.1. Notice it's going to be a negative number. Or negative 0.01, which is a little bit closer. Negative 0.001, so on and so forth. What were we looking for? We're looking for the square root of 2, which is roughly 1.41. Okay, well, it's an irrational number, so 1.41 itself is just an approximation. But based on the numbers we're seeing right here, it does make sense, and it does seem that we are approaching a value that looks roughly like the square root of 2. Now we also need to verify that we're approaching the same value from the other side, from numbers that are larger than 0. So how about 0.1, 0.01, a little bit closer, 0.001, there we go. And same kind of behavior, not necessarily the same values, but the same kind of behavior, approaching roughly 1.41 in the middle. So again, that's pretty good confirmation that this value for this limit makes sense. And again, even though this was an irrational function, this worked out the way it did because the value we were approaching was a value within the domain of this function. Now let's look at another example, truly a rational function with a numerator and a denominator. Now we know with functions that have a numerator and a denominator, there is the potential for certain issues to arise that we don't necessarily have with other functions. So as soon as there's a denominator, there is a risk for division by 0, which means something very specific algebraically and also very specific graphically. So let's see what happens in a situation like that from an algebraic standpoint. So this is a rational function. We want to find the limit as x approaches negative 3 of x squared minus x minus 12 quantity divided by quantity x plus 3. So based on the rule for something being in the domain, can we evaluate this limit by just plugging in? Well, what happens if we plug in negative 3, specifically in the denominator? Look at that. If we plug in negative 3 in that denominator, negative 3 plus 3 is going to evaluate to 0, which means we're now dividing by 0, which is undefined. It's not allowed. So in this case, just directly plugging in negative 3 is not going to work. It's actually going to be undefined, and so we can't find the limit that way. Now we can find it graphically, we can find it numerically using the techniques we already have, and then we're going to revisit the algebra. So let's type in this function, and let's see if we can find the limit using the techniques we already know. Now, as usual, make sure you have parentheses around your numerator and parentheses around your denominator. So there's your numerator divided by your denominator, x plus 3. Okay, and then we want to graph that. Okay, so notice it's not your standard rational graph. Something else is going on here. So let's look at the table for some actual values so we actually have something to graph. Now I'm going to go back into the table settings, turn it back on auto, so we have a little bit better numbers. Okay, so in this case at negative 3 we have an error. Normally error means a vertical asymptote if we're talking about a rational function. But here the error is a little bit different, and we can see what the error really means once we start to put in some additional ordered pairs and get a better sense of the graph. Based on the graph, it looked like a line, so what is an error going to mean in this case? Well, let's graph some ordered pairs that we do have. So negative 4 and then negative 8. Okay, there at negative 3 we have an error, but at negative 2 we are at negative 6, so 1, 2, 3, 4, 5, 6. Okay, they're at negative 1, we're at negative 5. At 0, we're at negative 4, so there's our y-intercept, and then so on and so forth, and we have all of those points in that particular line. So that's going to be our graph, but not quite, because remember there's an error there at negative 3. So we have a graph that looks linear, but where there would be a point at negative 3, there's actually a hole in this graph. So we'll indicate that by drawing a hole. So what's happening as we approach x equals negative 3, which is right here. So again, I'm going to put that dotted line. It's not an asymptote, but just so we know where we're looking and where we're looking from the left and from the right. So that's the location in question. We're looking at values to the left of that, values to the right at that. So as we approach this location from the left, from the negative numbers, our y values as we trace the graph approaching from this side are approaching a value of negative 7. Okay, so from the left we're approaching a value of negative 7 where there's a hole in the graph. From the right, now we're approaching from above, also approaching a value of negative 7, again where there's a hole in the graph. So graphically speaking, it looks like we potentially have a value of negative 7 for our limit. Now let's verify this numerically. Let's look a little bit more closely at values that are close to x equals negative 3. And so I'm going to change back my table settings, go back to ask for my independent variable, and so I can type in the things I want. I'm going to put numbers that are smaller than negative 3 up here and then larger than negative 3 below, like you would normally see them listed in the table on the calculator. So smaller than negative 3, those are things that are more negative. So negative 3.1, negative 3.01, negative 3.001, things like that. Things over here will be numbers that are negative but larger than 3. So negative 2.9 would be larger, negative 2.99 would be larger but a little closer, negative 2.999, again larger but even closer. Let's see what happens with those. Now what happens at negative 3? Let's confirm that. Well, we get an error. So remember there's nothing there, there's a hole there. So this is undefined. So we don't actually have a point there, and we already determined that by determining that we can't plug in -3 to this function. It forces us to divide by 0. What happens with these other values though? So -3.1, we're at -7.1. Okay, -3.01, we're at -7.01. -3.001, -7.001, and then so on and so forth. So from this particular side, which would represent the left-hand side of the coordinate plane, we're approaching a value of -7. Now what about the other side, the right-hand side? So -2.9, we are at -6.9. And I always like to start from the values that are further out. That's just a habit I've gotten into. -6.99, a little bit closer. Or sorry, not 6, 2. Apologies, -2.9. Delete, 2.99. There we go. -6.99. -2.999, even closer. -6.999. And so again, we see the same behavior approaching -7 from both sides. So that makes sense based with what we see from the graph. So initially it didn't seem like we can evaluate this limit algebraically, but as it turns out, we do have some other strategies. Initially, we'll try to do exactly what we did here, which is sub in a value. In this case, substituting in the value from the very beginning gives us something that's undefined. We have some other strategies as well, though. Another strategy to use is to use our algebraic techniques to potentially rewrite the function in an equivalent way. So let's rewrite the function that we had. So x squared minus x minus 12 over x plus 3. Okay. What I noticed looking at this function just structurally, its numerator is quadratic. I know quadratic trinomials can potentially be factored. So let's see what happens if we take a moment and factor this numerator. So we're looking for numbers that would multiply to give -12, that also add to give -1. So that would be -4 and +3. So that would be our two binomials that factor to give us that particular quadratic. And of course we can double check our factorization by redistributing. So x times x is x squared, and then 3x and -4x gives us -x. And then -4 times +3 is going to give us -12. Well, the benefit of doing that is notice we now have a common factor in the numerator and denominator, which means that then reduces to 1, and we're just left with x minus 4. So although the original function is a rational function, an equivalent way to write it is in the form x minus 4. Keeping in mind, however, that the original function had a denominator. This particular function by itself, which is linear, is defined for all real numbers. It can take any real number and we can evaluate it. But the original function that it was equivalent to could not be evaluated at -3. So we just have to keep that in mind in thinking about this as the actual function. But if you look at the function that we graphed, it looks like that line x minus 4. So an y-intercept at -4 and then a slope of 1. This would be the line that we get. Notice there's just a hole there at x equals -3 where the original form of the function was undefined. But this is an equivalent form. And notice in this case, using this equivalent form, if we were then to take the limit as x approaches -3, not of the original form for our function, but for the equivalent form of our function, we now have a form of this function where we can actually just plug in and evaluate with the x value that we're given. So -3 minus 4, which simplifies down to -7, which lines up with the other values we got for the limit graphically and numerically. So if we can manipulate what we're looking at algebraically ahead of time, we may be able to handle situations where just plugging in our x value is not an option. We may be able to find an equivalent form where we can plug it in. Let's look at another one that is irrational but also has a numerator and denominator. So we want to find the limit as x approaches 9 of 9 minus x divided by the square root of x minus 3. Now, if we were to attempt this algebraically from the very beginning, what happens? Imagine plugging in 9, so 9 minus 9 would be 0. The square root of 9, which would be 3, minus 3, would also be 0. So we end up with 0 over 0, which is undefined. So we can't just plug things in. Now maybe we can do some things with this one algebraically, but immediately looking at this one, I know it's probably going to be more complicated, number one, because of that square root. So if an algebraic technique fails here, this one may make more sense to evaluate either graphically or numerically, or potentially both, so that we have confirmation of what our answer should be. So let's see what this graph is going to look like. Okay, parentheses around your numerator, so 9 minus x, and then parentheses around your denominator, so the square root of x. Make sure after you type your radical, arrow out, and then type minus 3 so that it's outside of the radical. So double check you've typed exactly what you intend to type before you graph it. And there we go, that's what we have. So let's get some ordered pairs in order to actually generate this graph accurately. So I'm going to go into the table. Okay, we still have the values from before. So let's go back into the table settings, change it back to auto. Notice you're doing a lot of that, changing it from auto to ask. That's okay. Now we have a lot of errors. Why do we have errors? Well, look at the graph. Over here on one side of the function, or one side of the coordinate plane, excuse me, we don't actually have any function values. So that means there's a bunch of x values for which this function is undefined, specifically because of that square root in the denominator and the things we know about square roots. There are specific requirements. So it looks like 0, we're at negative 3. So 0, negative 3. Okay. Anything less than that, less than x equals 0, we have an error, so there is no graph over on the left-hand side of the coordinate plane. Now when we're at 1, we're at negative 4. Okay, let's see, 4, negative 5, 1, 2, 3, 4, 5. Just graph the points that are easy to graph. Now we're interested in x equals 9, so ideally we want to get some values that are out near there. Now at x equals 9, we have an error, which means in this case there's going to be a hole. But what's happening on either side of 9? That's the question we want to ask. So there at x equals 8, we're at about negative 5.8. So x equals 8, we're about negative 5.8, so somewhere like that, roughly. And then at 10, on the other side, we're at negative 6.162, so a little bit more negative than negative 6. And so if we meet in the middle, it looks like we're probably meeting at about right there. But again, there's an error, which means there's a hole in this case. There is not an asymptote, there's a hole. So we end up having roughly something that looks like that. Of course, graphed a little bit better than how I graphed it. Okay, so what's happening here? As we approach 9, which is right here, as we approach 9 from the left-hand side, our graph traces this way, and it looks like it ends up at about negative 6. That's where we have the hole. And as we go from the other side, same idea. We also trace that, and it looks like we also end up at that hole at roughly negative 6. So based on the graph, it looks like we should have a limit somewhere around negative 6. Let's confirm that with the table. So around 9, numbers that are smaller than 9, numbers that are bigger than 9 but close to 9. So smaller than 9, we could have 8.9, 8.99, 8.999, and then bigger than 9, maybe 9.1, 9.01, 9.001. Okay. Now at 9, remember we determined it is undefined. There's that hole in the graph, and when we try to substitute in 9 at the very beginning, we end up with a number that is undefined. So let's change the table settings to get those numbers that we want. So I'm going to change it to ask, go back into my table, and then we want to evaluate with these values. So at 8.9, negative 5.983, 8.99, negative 5.998, and then 8.999, we're at negative 6, but not quite negative 6. So close to negative 6 that your graphing calculator says it's negative 6. But again, keep in mind there are limits in terms of how many decimals your calculator can type, which is why it has negative 6 there as opposed to negative 5 point something. Okay, now what about the other side? 9.1. So negative 6.017, 9.01, negative 6.002, and then 9.001. Again, same kind of thing. It's not truly negative 6, but it's so close that your calculator can't handle the decimals that go with that. So from one side, we're approaching negative 6. From the other side, we're also approaching negative 6, which confirms what we see from the graph. So the value of our limit will be negative 6. Okay, let's look at one additional example where maybe we run into some issues algebraically. So slightly more complicated, still a function that has a numerator and denominator, so the same kind of problems we normally see we anticipate with a function that looks like this. Okay, so we want to evaluate the limit as x approaches 2 of x squared plus 3x minus 10, quantity, divided by the quantity x squared minus 4x plus 4. So let's start off by trying the algebraic technique. What happens if we sub in 2? So let's focus on the denominator. So 2 squared would be 4. 4 times 2 is 8. So 4 minus 8 would be negative 4, and then negative 4 plus 4 is 0. So the same issue we've seen before we see with this function right here. Okay, so we know we can't just directly substitute in 2. We may have to do a little bit more work with it in order to evaluate this limit. So let's evaluate it graphically and numerically again like we've done for the others. So type in the function. So we have x squared plus 3x minus 10, all in parentheses, divided by x squared minus 4x plus 4. Okay, so more what we're used to seeing with an actual rational function with its graph. Let's go into the table. Now we need to change the table settings back to auto again. Let's get some ordered pairs so we can graph. Okay. Now, I want to look for some of the errors though. Remember, those are your asymptotes. We know we have an asymptote here. It looks like it's at x equals 2, and that's also where we're evaluating our limit, so not surprising. So there at x equals 2, that's where we have our vertical asymptote. Now we also have a horizontal asymptote here when we compare the degree in our numerator and denominator. The degrees are the same, both have a highest exponent of 2. So the horizontal asymptote is going to be the ratio of the leading coefficients. In this case, there's an understood 1 in the numerator and 1 in the denominator. So if we take the ratio of those two numbers, that's going to be 1. So our horizontal asymptote is going to be at y is equal to 1. So that's going to be the other boundary that we see on that graph. Okay, now let's get some actual ordered pairs. Specifically, we want to focus on left of the asymptote and right of the asymptote. Make sure we get both sections. So the asymptote is there at x equals 2. So to the left, when x equals 1, we're at negative 6. When x is at 0, we're at negative 2.5. That's not too bad to graph. So there we go. Any other good points to graph? Let's see. Anything easy? Negative 5, 0. That's a good one. And that should be enough. We're just going to hug those asymptotes. Okay. And you do a better job than I did of connecting those dots. Now to the other side of the asymptote, when we're at x equals 3, we have a y value of 8. And then when we're at 4, we have 4.5. So 1, 2, 3, 4.5. Let's see if we can get something else. There we go, 9, 2, that's pretty good. So 9, 1, 2. And again, connect the dots following those asymptotes. And there we go. And that looks pretty consistent with what we see on the graph. Okay, so we're evaluating the limit as x approaches 2. We need to look at the left-hand side. We need to look at the right-hand side specifically of this asymptote. So as we approach 2 from the left-hand side and trace the graph, following the graph as we approach 2 from the left, the graph dips down and we go towards negative infinity. So as we approach 2 from the negative side, it looks like our left-handed limit goes towards negative infinity. Now what about approaching 2 from the right-hand side? Okay, well, as we approach from the right-hand side, trace that portion of the graph. We're unbounded and we go up towards positive infinity. So our right-handed limit goes to positive infinity. So because the left-handed and right-handed limit approaches 2 different values, that means our general limit does not exist, at least based on what we're seeing from the graph. So supposedly, graphically speaking, that confirms that our limit does not exist. Now, are we going to see that numerically? We should. Let's verify that we do. So I'm going to go ahead and change my table settings back to ask. We want to look at numbers on either side of 2. Go back into the table. So numbers that are to the left of 2, smaller than 2, and numbers that are bigger than 2. So we'll say 1.9, 1.99, 1.999, 2.1, 2.01, 2.001, and then let's evaluate with those. So 1.9, we're at negative 69. 1.99, we're at negative 699. And you can probably guess what's going to happen with the next one. Negative 6,999. So what's happening? Our numbers are getting larger and larger, but they're negative, which is exactly what we expect as we go down towards negative infinity, approaching 2 from that particular side. So in this direction, we're approaching negative infinity. So as we approach 2 from the left, our function values are going towards negative infinity. Now what about approaching 2 from the right? So if we're at 2.1, our function value is 71. 2.01, we're at 701. And again, you can probably guess what's coming next. 2.001, 7001. So again, getting larger and larger as we approach 2 from the positive side, our numbers are going up towards positive infinity. So because we're not meeting in the middle at that common value, because our 2 limits, the one on the left, the one on the right, approach different values, also confirmed the limit does not exist. And again, we know at 2, of course, it is undefined. That is where we have that asymptote. Now, what does the algebra say? The initial algebra just said we can't plug in 2, it's undefined at 2, we know there's an asymptote at 2. But just like with a previous example, I'm looking at this numerator, I'm looking at this denominator, they're both quadratic trinomials. I know we potentially have an opportunity to factor, so let's see if that puts us in a better position algebraically. So our numerator was x squared. Let me verify. X squared plus 3x minus 10. Okay, and then our denominator was x squared minus 4x plus 4. There we go. X squared plus 4x, minus 4x, excuse me, minus 4x plus 4. That makes more sense. Okay. So let's see if we can factor this numerator and denominator, and maybe there's something common that cancels just like it did before. So in the numerator, we want numbers that multiply to give negative 10, that also add to give positive 3. So that would be positive 5 and negative 2. And then in our denominator, we want numbers that multiply to give positive 4, that also add to give negative 4. So that would be negative 2, but twice. So as suspected, we do have a common factor that reduces to 1. And now we're left with x plus 5 divided by x minus 2 as an equivalent form of our function. So let's see what happens with our limit now. We were evaluating our limit as x approaches 2, and now we're going to evaluate using the simplified form of our function. But what happens now? Well, notice our denominator is now x minus 2, which is simpler than the original. But if we sub in 2, just as we would normally do algebraically, we still have a denominator of 0. It's still undefined. So in this case, again, the limit does not exist. We're left with something that cannot be evaluated at that particular value, and the numerical and graphical techniques confirm that this limit does not exist. So when in doubt, we typically want to evaluate limits algebraically when we can, because in most cases they will save us time evaluating our limits that way, but we do have numerical and graphical techniques to fall back on when the algebraic techniques are not an option. So now let's talk about continuity. Continuity is something that you can intuitively understand just looking at a graph, but we can understand it in a little bit more detail, a little bit more formally, now that we have a sense of what a limit is and we know what the term limit means. So intuitively, a function's graph is continuous over an interval, specifically an interval of the domain, if it can be traced without lifting a pencil or whatever writing utensil you're using. So that's the intuitive idea of something being continuous. No holes, no breaks, nothing like that. If you could trace the whole graph without lifting your pencil, then it's a continuous graph. If there is some point in the interval where there is a hole, or maybe a jump, if you want to call it that, then the function is discontinuous over that interval. Specifically, it's discontinuous at that point, but because we're looking at a point within an interval, it is going to be discontinuous over that interval because there is a discontinuity. So the individual location where suddenly there's a hole or a jump is what we call a discontinuity in the graph and hence in the function. So if we already have a picture of our function, if we already have a graph, continuity is pretty easy to determine. But the idea is we want to take it one step further, and suppose we don't have a graph. Suppose it's not a function that we can easily graph. Maybe we can't get a picture very easily. Well, as it turns out, we can actually determine whether or not our function is going to be continuous at specific locations just using what we now know about limits. So some examples of discontinuities. They can look a variety of different ways, and we have discontinuities from a formal standpoint for different reasons of each of these, for each of these. So this particular function, this is an example of a rational function. Here's the actual function rule that generates the graph. Okay, and we very clearly have a vertical asymptote at x equals 3. So our discontinuity is at x equals 3. So there's a few things going on here. What I want to pay attention to is, number one, the function value, what happens to the actual function at that location. And then number two, what can we say about the limit at that location? Or more specifically, what happens to the left, what happens to the right at that location? So number one, f of 3 is undefined. We can officially say that. If you try to sub in x equals 3, the function is undefined. So number one, there isn't even a point there at x equals 3. There's a big gap in the graph. Now what can we say about the limits? Specifically at 3. So if we approach 3, but from the negative side, if we're taking our function and we're approaching 3 from the negative side, then our function values are decreasing without bound. So that limit is going to be negative infinity. And if we take the limit as we approach 3 from the positive side, then we trace this graph and we're unbounded, increasing. So we're going towards positive infinity. So if we put these two one-sided limits together, because they each approach different values, then we can say that our general limit as x approaches 3 of our function does not exist. So we had two issues here with this particular graph resulting from this particular function. Number one, it's undefined at a particular location, and at that same location, the limit does not exist. So we're approaching different values from the left and from the right. So two potential issues here that affect continuity. Now this is a very different situation, a very different kind of graph, and this is the function that represents that particular graph. So what can we say here? Where is there a discontinuity here? Well, if you follow the linear graph, there's a hole right at this location, and then we jump. So the actual point is right here, and then what would be the associated point on the linear graph, there's actually a hole there. So what can we say about the function value there at that particular location, which is going to be x equals 2? Number one, notice this is a piecewise function, and x equals 2 is the location where we change from one rule to another. So if x is 2, we're following the first rule, and then for any other x value not equal to 2, we're following the other rule. So what can we say about g of 2? Well, g of 2, when x is 2, when we're subbing in a 2, this rule tells us that the output is going to be 5. Okay? So it is defined, the function is defined at the discontinuity. What can we say about the limits? Well, the limit from the left-hand side of 2, if we take the limit approaching 2 from the negative side for this function, let's just base it on what we see on the graph. As we approach 2 from the negative side, we're approaching a y value of 3. So the limit for our function as we approach 2 from the negative side is going to be 3. What if we approach from the positive side? So the limit as x approaches 2 from the positive side for our function, also approaching the same value. So as we trace the graph approaching x equals 2, we also approach that location there at 3. So in this case, the left-handed limit is 3, the right-handed limit is 3. So we can say officially that the limit, the general limit, as we approach 2 for our function, it does exist, and specifically, it has a value for 3. So what's the problem here? The function is defined at the discontinuity. The limit is also defined. The problem here is that the function value and the limit value are not the same. That was why we had a discontinuity there. So a bunch of things were defined, but if our limit and our actual function value differ, that also represents a situation where we have a discontinuity. And again, here the discontinuity was at x equals 2. Let's look at another example of a discontinuity. Also from a piecewise function, but this piecewise function looks a little bit different than the previous one. Here, rather than having just one location where we jump and then otherwise following the same rule, one interval is represented by one particular rule, and then another interval is represented by another function rule. So where is the discontinuity here in terms of the x values? Well, it's definitely here at x equals 1. And notice that's also where we change from one function rule to the next. So again, we want to investigate the same things. What happens in terms of the function value at that x value, and what happens in terms of the limit at that x value. So the function value, h of 1, number one, does it exist? Well, there is a rule corresponding to x equals 1. When x equals 1, we follow rule 2. So if I sub in a 1, 2 times 1 is going to be 2, 2 minus 2 is going to be 0. And that's actually confirmed from the graph as well. So here's the actual point at x equals 1. The associated y value is 0, so h of 1 is going to be 0. Now what about the limit, specifically from the left and from the right? So the limit as x approaches our discontinuity, 1, from the left-hand side. Notice for that particular section, we're using the first rule. So we're following this portion of the graph. Well, as we approach x equals 1 from the left, trace the graph towards that location, it looks like the y value we get close to is going to be y equals 4. So the limit as we approach from the negative side is going to be 4, because that's the function value we approach as the x values get closer and closer to 1 from that direction. What about the positive direction? Well, now we're looking at another function rule. We're referencing different x values, hence a different function rule. So in this case, as we approach from the right, we're following this portion of the graph. And as we follow this portion of the graph, we end up approaching a y value of 0 as we get towards x equals 1. So in this case, the y value is 0. So what can we say about the limit in general? Well, from the left we approach 4, from the right we approach 0. So because we approach different values, the general limit as x approaches 1 of our function h of x does not exist. So the function is defined at its discontinuity. Okay, the one-sided limits exist, and one of them even matches up with that function value, but the actual limit, the general limit, does not exist because we're approaching different values from the left and from the right. So all three of these different situations represent different kinds of discontinuities. The biggest thing again is we're looking at the function value and we're looking at the limit. So in all of these situations there were discontinuities, but there were discontinuities for different reasons. So to understand why there were discontinuities there, it's going to help to define what continuity looks like. When is a function continuous at a particular location? And then of course if these conditions are violated, that means we then have something that is discontinuous. So a function is said to be continuous at a specific value, not over an interval, but at a specific value that we're going to call a. It's continuous at x equals a if three conditions are met. So number one, first off, f of a exists. The function value at that x value exists. In other words, there's nothing like an asymptote, there's no hole there, nothing like that. So that means the output at x equals a exists. That's the first requirement. So which functions violated that rule? Well, it looks like the first one violated that rule because our function value was undefined at that location. That automatically meant that we had a discontinuity. We weren't continuous there at that value. Okay, that's not enough though. We have additional requirements. So in addition to the function value existing, the limit as we approach that value, and the general limit, not just left hand, not just right hand, but the general limit for the function at that value also exists. So the limit as x approaches a exists. Where did we have an issue with that? Well, in this particular case, the function value existed, but because we were approaching two different values, one from the left, one from the right, the limit didn't exist. So that was representative of that discontinuity. And the last situation, the last requirement to have continuity is that these two have to be the same. So not only does the function value exist, it's defined for that particular value of x, the limit exists, which means we approach the same value from the left and the right. Those have to represent the same value. So whatever f of a is, whatever the limit is, both existing, they also have to be the same. So we also need that the limit as x approaches a of f of x, it also needs to be the same as whatever f of a is. So in other words, the limit is the same as the output. And that was the condition that was violated for that second graph. So that second graph was almost continuous. It was almost just a line, except we had a jump right there at that one location. So the function value existed, the limit existed as well, but they didn't have the same value. So because they had a different value, our function was approaching different things from the left and right, but the actual function value jumped and took us somewhere else and then represented a discontinuity. So all three of these conditions must be met in order to say that we are continuous at a particular point at a particular x value. So we can extend that. We can say that a function is continuous over an entire interval, a range of x values. We're going to call that I. That interval is I. If it is continuous at every value in I. So if we wanted to say that a function is continuous over all real numbers, then that means we have to have continuity at every single individual point. If the function is not continuous at a particular value x equals a, in other words, one or more of these requirements is not satisfied, then we say that a represents a discontinuity in the function. And again, if we're looking at a within the context of a particular interval, if it's a discontinuity, and within the context of that interval, we could say that our function is not continuous over that particular interval because it has a discontinuity at that particular value of x. So let's try a few examples justifying continuity or discontinuity. So first example, is the function given by f of x is equal to x squared minus 5 continuous at x equals 3? And we want to justify it, which means we need to verify that all these criteria are met or determine that one or more is not met. Now, first off, this is a polynomial function, and in general, polynomial functions are continuous over the whole real number line, if you think about what a polynomial function's graph looks like. But let's go a little bit further and let's prove this using these three criteria. So what do we need to do? Well, number one, we need to determine, is the function defined at 3? Make sure that f of a, in this case f of 3, exists. Number two, we need to make sure that the limit at x equals 3 exists. And we can do that numerically, we can do that with a graph, we can do that in a couple different ways. And then also we need to make sure that, number one, it exists, and number two, they're the same. They need to have the same value. So let's start with f of 3. Make sure that we know that exists, make sure we know the value. So f of 3 is going to be 3 squared minus 5, which is going to be 9 minus 5, which is 4. Okay, so the first criterion is met. The function value does exist. Well, now we need to determine if the limit exists. So the limit as x approaches 3, okay, of f of x, what is it? Does it exist? If so, what is its value? So let's do this algebraically, again using our table, using the graphing capabilities. So we have x squared minus 5. Let's graph it. Well, it doesn't look like there are any holes, but we've seen plenty of graphs at this point where it doesn't look like there's a hole, but maybe there is. So we need to see what's happening to the left of 3, to the right of 3. And I'm going to change my table settings back and forth so that we have a nice clean table. Go back into ask. Okay, and then we want to go into the table. Okay, so it looks like it's continuous at 3. Let's verify that by checking this limit. So we want numbers that are less than 3 and numbers that are greater than 3. So less than 3, maybe 2.9, 2.99, 2.999. Okay, we could keep going. What's happening? Well, it looks like we're getting closer and closer and closer to 4. Okay, let's verify that the same thing happens on the other side. So above 3, so 3.1, 3.01, 3.001, 3.0001, so on and so forth. Again, it also looks like we're approaching 4. So because we're approaching this common value from both sides, we can say that the limit does exist and its value is 4. So in this case, this is criterion 1. That's checked. The limit does exist. Check. And then our last criterion, are they the same? Do they have the same value? So the function value and the limit, in this case, they do have the same value. So the limit as x approaches 3 of f of x is also equal to the function value at that particular location. So based on all three of these criteria being met, we can say that our function is continuous at x equals 3. Okay, let's look at another one. Now this one was polynomial, so intuitively it should be continuous. It's not as obvious when we're talking about something like a piecewise function. So we want to know, is this function continuous at x equals -2? Why would -2 be a potential location for discontinuity? Well, it's the location where we jump from one rule to another within our function definition. So the individual functions, the individual function rules are both individually polynomial, so they'll be continuous over their own domains. But where we jump from one rule to another, we potentially run into an issue. So we need to verify that we are in fact continuous, that we meet all these criteria. So number one, we need to evaluate our function, make sure the function value exists at -2. So which rule do we follow at -2? Well, here x equals -2. That means we're going to follow the second rule. So -2 minus 1 will be the rule we follow, which means our function value exists and it has a value of -3. Okay, now we need to check our limit. Now here, because we have two different rules, this rule applies for numbers that are smaller than -2, in other words, the left-handed limit. This rule applies for numbers greater than or equal to 2, in other words, the right-handed limit. So we'll have to analyze each of these individually. So we want the limit as x approaches -2 from the negative side for our function. Okay, so from the negative side, we're using that first rule. So let's type in the first rule and see what happens. So 0.5x plus 3. Okay, now remember, we're only going to keep the portion of that graph corresponding to x values that are less than -2. So the right-hand portion of that graph would be dropped off. So let's look at the table, and you can clear it if you want, or you can just type over things if you want as well. So we're approaching -2 from the negative side. We're looking at values that are smaller than that. So from the negative side of -2, that's numbers that are smaller, that are more negative. So something like -2.1, -2.01, just a little closer. Oops, delete, enter. -2.001, so on and so forth. It looks like as we get closer and closer to -2, we're getting closer and closer to +2 as a limit. Okay, what about the right-hand side? So the limit as x approaches -2 from the positive side for our function. Well, if we're approaching from the positive side, now we're following the other rule. So let's type in that rule. So the next rule is going to be x minus 1. Okay, there's its graph. Again, we only want the portion corresponding to x values greater than or equal to -2. And let's look at the table. So now we're looking at approaching -2 from the right-hand side, from numbers that are larger than -2. So something like -1.9, -1.99, -1.999, so on and so forth. And so based on those values, it looks like we're approaching a value of -3. So the left-handed limit exists. It approaches a value of 2. The right-handed limit exists, approaches a value of -3. But these two values are not the same. So in this case, the general limit as x approaches -2 for our function g of x does not exist. So that would be criterion 2. The limit must exist. In this case, because the limit does not exist, we can confirm that this function is discontinuous. It is not continuous at x equals -2. Okay, let's look at another one. Okay, another piecewise function, a little bit more complicated. So one of the rules is just a constant. The other rule is a rational function. So we want to know, is this function continuous at x equals 4, again, where we have that break, where we have the potential for a discontinuity. Now, what happens exactly at x equals 4? Well, we can't evaluate this particular rule at x equals 4, because if we tried to plug it in, that would give us a 0 in the denominator. So this function is telling us that at x equals 4, we're going to jump to an output of 7, and then for the rest of the domain, we'll follow that original rational function. Okay, so what is h of 4? Number one, does it exist? Let's determine that. So h of 4, if we evaluate the function for an input of 4, that automatically means the second rule applies, and the second rule is going to give us an output of 7. So the function value does exist. That's criterion 1. What about the limit? What's going to happen to the left of 4? What's going to happen to the right of 4? Well, as we go towards 4 from the left and the right, we're following this rule. So the general idea is right there at 4, we have one particular rule, but anywhere else, including both the left-hand side and the right-hand side, we're following this other rule. So as we evaluate the limit, we're looking at this other rule, the rational rule. Let me verify that that is in fact the correct rule. Somehow this got cut off. This should be a 16. So let's verify that that is correct. Otherwise this is going to be a pain to evaluate. Okay. So in this case, we can look at this from the graphing standpoint, or number one, I know I can't evaluate it at 4 because I can't just plug it in, but we talked about this earlier in the video. If we can take something like this and simplify it, we may have some other options for evaluating our limit algebraically, which will save us some time. So I noticed that numerator is a difference of squares, so it's going to factor as x plus 4 and x minus 4. And so in that case, we have a common factor that cancels with our denominator. So a reduced form of our expression is going to be x plus 4. So that means in evaluating the limit, since we're going to use that particular rule both for the left-hand side and the right-hand side, we can use this particular rule instead. So the limit as x approaches 4 from the negative side, and now again we're going to use this, that's going to be x plus 4. Okay, imagine approaching from numbers that are smaller than 4, so something like 3.9, 3.99, 3.999. What are we getting really close to? Well, eventually we're going to get to about 8, right? So something smaller than 8, then a little bit bigger, then a little bit closer, then a little bit closer. As we approach 4, 4 plus 4, we could plug that in. In that case, that would be 8. And the same will hold true approaching from the right-hand side. If we add something a little bit bigger than 4, 4.1, 4.01, 4.001, we are approaching a value of 8. So the left-handed and right-handed limit are the same. So in this case, the limit does exist. So the limit as x approaches 4 in general for our function, not just for x plus 4, but for our actual function, is going to have a value of 8. So our function value exists, our limit exists, but in this case, they are not equal to the same value. So the limit as x approaches 4 for our function, h of x, is not equal to the function value at that particular x value. So that means criterion 4 is not met. It means we are discontinuous at x equals 4. Okay. one more example, one more. Now let's take it up one notch. So here we're being asked a slightly more complicated question. The question is the function, this piecewise function, again, continuous for all x? And we want to justify, is it not, using those three criteria. Okay, so for all x means any x value we have to be continuous at. So most importantly, we want to identify any locations where there is potential for a discontinuity. So let's start by looking at the individual function rules themselves. So the first rule is linear. If we were to graph that particular function rule, it would just graph as a line. Well, a line is going to be continuous over its whole domain, so we shouldn't have any discontinuities just by the nature of the function rule for the first one. The second one is quadratic, same kind of situation. There's no discontinuities inherent in that function rule. So the only location where we would potentially have an issue is at the location where we jump from rule 1 to rule 2, which in this case is at x equals 2. So the question is, what happens at x equals 2? Since these two function rules by nature are going to be continuous for any value you plug in, the only location where we potentially run into an issue is where we jump from one graph to the other. So that's what we need to investigate, what's going to happen there at 2. So just to be a little bit more formal about this, we can say that negative x plus 3 is continuous on this whole interval from negative infinity to 2. Okay. We're again investigating what happens at 2, so I'm not going to put a bracket. I'm going to leave it as parentheses. That's saying all the way from negative infinity up to 2, we know that this function is good. We know this rule is good, so we should be okay there. Now the next function rule, x squared minus 3, is continuous for everything greater than 2. So for 2 to infinity. So the question again was, is the function continuous for all x? Well, based on the function rules, we're okay from negative infinity to 2. We're okay from 2 to infinity. Again, the question is, what happens at 2? Are we okay at 2? So let's go through our list. First thing, we want to evaluate f of 2. What happens there? Well, in this case, the rule that applies for 2 is going to be the first rule. There's x equals 2, so we're going to follow that first rule. So that's going to be negative 2 plus 3, and the negative 2 plus 3 is going to be 1. So criteria 1 is met. We do have a function value at that location. Now, what about the limit? Because we have two different rules, we need to analyze left-hand side, which is the first rule, and then right-hand side, which is the second rule. So the limit as x approaches 2 from the negative side. Well, here, because this particular individual rule is rational, we can sub in, just like we would do with a single algebraic function by itself in order to evaluate our function or our limit algebraically. But we are specifically using this first rule. So the limit of our function as we approach 2 from the left-hand side, we can evaluate using that first rule. So that's going to be negative 2 plus 3, which again we determined was positive 1. As we approach from the right-hand side, we're now analyzing with that second rule. So the limit as x approaches 2 from the positive side for our function. Again, we can sub in a 2. We don't have any issues there, so we can evaluate our limit algebraically. So 2 squared minus 3, that's going to be 4 minus 3, which is 1. So the left-hand limit has a value of 1. The right-hand limit has a value of 1. Because those are the same, we can say that the general limit as x approaches 2 for our function is also going to have a value of 1. So our function value exists, our limit exists, and they have the same value. So the limit as x approaches 2 for our function f of x is also equal to f of 2. which is our requirement to say that all three of these are met. That's our requirement to say that we are continuous. So because of this conclusion, we are continuous at that one location. That proves that we're continuous at x equals 2. So we're good from negative infinity to 2. We're good at x equals 2. And we're also good from 2 to infinity. So based on those three items, that tells us we are continuous for all x. So we can confirm that. All x, all the way from negative infinity to infinity. So this gives you another perspective on the issue of continuity. Again, continuity is pretty intuitive, specifically when we're looking at a graph, but if we don't have a graph, if we're just looking at a function, maybe something that is difficult to graph, continuity can be explored in a variety of different ways. So I definitely encourage you to use these three limit evaluation techniques flexibly. Make sure you're comfortable with all three. Again, algebraic evaluation is typically going to be your easiest option. It's typically going to be faster than anything else. But in general, you can think of numerical and graphical evaluation as backups and as good ways to check your work.